Okay, now in this lesson 24, we're going to use the method of Laplace transforms to solve some differential equation problems, some initial value problems. Um, the usefulness of the Laplace transform for the purpose of solving differential equations rests primarily on the fact that the transform of the nth derivative is related in a very simple way to the transform of the original function f. So here's what the theorem says that allows us to use the Laplace transform to solve the differential equation. It says, suppose that you have a function that is n times differentiable, so the derivative exists and you can take it n times, and suppose that the nth derivative is piecewise continuous from 0 to infinity. So if the derivative exists actually n plus 1 times, then that will be automatically satisfied because if a function is differentiable, then it is automatically continuous. And if it is continuous, then it's automatically piecewise continuous. Okay, anyway, suppose the function is differentiable n times and the nth derivative is piecewise continuous. And suppose further that all the derivatives are exponentially bounded. So this condition right here is usually abbreviated by saying the derivatives are exponentially bounded. That basically means that functions don't grow too quickly. They don't grow faster than some exponential function times a multiple, uh, constant multiple. So they don't grow too quickly. Okay, so they're exponentially bounded, and that is true for all the derivatives. Okay, all the way to the n minus one. Well, the theorem says that if these conditions are satisfied, then the Laplace transform of the nth derivative actually exists, and all the previous ones as well. So the Laplace transform of the n minus one's derivative also exists, and actually all of them. And moreover, there's a neat little formula that allows you to express the Laplace transform of the nth derivative in terms of the Laplace transform of f without derivatives, just the original f, and the derivatives at 0. So this formula right here is very, very important. So, I mean, this is the formula that will allow us to solve differential equations using the Laplace transform. It looks convoluted, but it is just it follows easily, actually it follows really easily by just using integration by parts over and over. So as many times as you need to. So if n is 4, you just do integration by parts 3 or 4 times. So it is not really hard to come up with this formula. And even though you don't have to memorize it, um, two things, you might end up memorizing perhaps the first two cases, n equals 1 and n equals 2, by the sheer number of times that we're going to be using it. And second of all, um, there's actually a very easy pattern. And I mean, you don't have to memorize it again, but if you were to memorize it, there's a very easy pattern that you can recognize here. So the Laplace transform of the nth derivative is s to the n times the Laplace transform of f. So that is always going to be there. And then all the other terms are minuses. Minus, 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 minus. All of them are minuses. And you see the exponents of the s start decreasing from n. And this n is the same as that n, the nth derivative. All the exponents of the s start decreasing, n minus 1, n minus 2, n minus 3, all the way to 0. 0 meaning s to the 0 is 1, so you don't write it. But you decrease all the way to 0, and at the same time, the derivatives start increasing. So you start with the zeroth derivative, the do nothing derivative, so that's the original function. First derivative, second derivative, third derivative, fourth derivative, all the way to the n minus 1 derivative. And there's one more thing to notice. The exponent of the s and the order of the derivative, when you add those two numbers, they always add up to n minus 1. So n minus 1, 0, added up gives you n minus 1. N minus 2 plus 1 gives you n minus 1. N minus 3 plus 2 gives you n minus 1, etc. The pattern continues all through the formula. So there's some pattern in there that if you wanted to memorize it, is not hard to memorize. But you're going to have this sheet that has all these formulas. So here's the sheet that you're going to have, and on the test day, so you should find a way to either print this or I don't know, copy it by hand or something. But you're going to have these table of Laplace transform. So whenever we need to know the Laplace transform of a function, we're just going to look it up in here. So these tables reads the Laplace transform of 1 is 1 over s. We did this. The Laplace transform of the exponential function e to the at is 1 over s minus a. Again, we also did that one. We did also number 5. The Laplace transform of sine of at is a over s squared plus a squared. We figured that one out. That requires integration by parts twice. Remember, we used the formula. I didn't do the actual integration by parts. I just said, okay, this is what you get if you do integration by parts twice. So it's not so easy, but we can, from now on, we can just look it up here. We don't have to do it all over again. And the Laplace transform of the cosine, and all of these, you have combinations of e's and sines, e's and cosines, polynomial t to the n and an exponential, and so on. And the formula that I just talked about is this one right here, number 18. The Laplace transform of the nth derivative is blah blah blah, and here you have the formula. And note that all these are little f's, and this one is capital F. Capital F, remember, is the Laplace transform of the little f. So it is that. Okay, anyway, you really need to either copy this or print it, because I'm going to be making reference. I'm going to be referring to this all the time. So whenever I say, okay, let's look up the Laplace transform of the cosine, I'm going to look it up here and say by formula number 6. So that's how I'm going to refer to it. You get the Laplace transform is blah. And on the test, I also want you to tell me which number you're using. Whenever you use a Laplace transform, you look it up in here. I want you to tell me you use number 6, number 8, number whatever. So I'm going to be making note of that on the problems as we solve them. Okay, and before we solve the first problem, let me point out some pros and cons of the Laplace transform. So here are the main advantages of the Laplace transform for solving IVPs, initial value problems, for linear differential equations that have constant coefficients. So this is another method. Now, the problem of solving the DFQ, the IVP, the problem is reduced from a DFQ's problem to a college algebra problem. Well, college algebra, sort of, because you still have to know how to do partial fractions. And you don't cover that in college algebra. But it's solved from a DFQ problem, it's reduced from a DFQ problem to an algebraic problem, where there's no derivatives or anything anymore. It's just algebra. So that's one advantage, because doing just pure algebra is easier, right? So you reduce a DFQ problem to an algebra problem. So that's good news. Another advantage is that the particular solution satisfying the given initial conditions is automatically found, automatically at once. You don't have to find the general solution, with C1, C2, C3 in there, and then uh, start plugging in so you can find C1 and C2 and C3 and get a system of equations and try to solve that. That you don't have to do any of that because the C1s, the C2s, and the C3s are automatically found by this method. So it does both in one shot. Solve the differential equation and find the C1s and C2s and C3s. So kills two birds with one stone. Another advantage is that it is not necessary to solve the associated homogeneous differential equation first, and moreover, non-homogeneous equations are handled exactly the same way. You don't have to do this if it is homogeneous and then do that if it is non-homogeneous, or do the homogeneous case first and then handle the non-homogeneous case. You can do the method works exactly the same without change for both types. Nothing changes. And the next pro is that the method can be applied in exactly the same way without modifications to differential equations of higher order. So it doesn't matter if it's order 1, order 2, order 3, order 4, order 10. It's done exactly the same way as long as all the Laplace transforms are satisfied. Exist, which are guaranteed by these conditions. Uh, so the function is n times differentiable, the nth derivative is piecewise continuous, and the derivatives are exponentially bounded. Now, in this class, you don't have to worry about checking all of those conditions because we're only going to be working with elementary functions. So that those conditions are going to be satisfied. So you don't have to worry about that. But normally, those are the requirements. All right. So the last pro was that the method can be applied in exactly the same way, regardless of the order of the differential equation. Okay, and now here's the con. The main difficulty when using the Laplace transform method occurs when uh, we want to invert the Laplace transform. So the thing is, we're going to um, apply the Laplace transform. So it's going to translate the problem from a difficult problem to an algebraic problem. And then we solve that algebraic problem, and then the main difficulty is in translating back to the difficult. So once you solve the algebra problem, you need to go back and translate it. You need to translate it back to a difficult interpretation, so you can tell me what the solution is. And that step is called inverting the Laplace uh, transform. So this problem is known as finding the inverse, solving the inverse problem for the Laplace transform. Because um, we're gonna end up with an expression that corresponds to the Laplace transform of some function, and that function that we don't know what it is the actual solution of the DFQ. So the problem is then trying to figure out what is the regional function for which what we have in front of us is the Laplace transform. And that is not always easy. It can be a little bit tricky. Okay, so the inverse. So if I give you the Laplace transform of something and I ask you what is the original function, then that's called finding the inverse Laplace transform. So inverting the Laplace. The function in that context is called the inverse Laplace transform. And one good thing about one piece of good news is that the inverse Laplace transform operator is it also behaves like a linear transformation. So it has the property that I told you about lesson 23, like it behaves like an integral. So you have um, so if you're trying to find the inverse Laplace transform of the sum of functions, oops, let me write that again. If you're trying to find the inverse Laplace transform of a sum of two functions, then you can just do each piece individually. I should probably have written that here. The Laplace transform of f of f plus g of s is just the Laplace transform of f of s plus, the Laplace inverse, the inverse Laplace transform of g of s. Okay, and it also works constant. You can also pull them out. So if you're trying to find the inverse Laplace transform of c times some capital F, you can pull out the constant and say, just worry about the rest. Okay, so that is true. So that's going to help us simplify the problem of trying to go back and find the inverse Laplace transform, which is going to be the solution to the DPQ. Okay, now we can solve the first problem. And here it is. Let's solve this differential equation using the Laplace transform method. Okay. Solving a DPQ using the Laplace transform method, getting it started is really easy. So here's how you get it started. So all you have to do to get it started is you're going to take the Laplace transform on both sides of this equation. So just apply Laplace transform on both sides. That's how you get it started. So that means we're going to get Laplace transform on the left side is Laplace transform of y double prime minus y prime minus 2y equals the Laplace transform of 0. Okay, so just apply L to both sides. Apply the Laplace transform operator to both sides. And now we're going to work out both sides. The left-hand side, we're going to work it out using the linearity properties. So this is the Laplace transform of y double prime minus the Laplace transform of y prime minus, you can write the Laplace transform of 2y, but you see 2 is a constant, so you can pull it out of there. So I'm just going to write the 2 outside. The Laplace transform of y. Using that property of linearity, you can pull out constants. Equals, and now, what is the Laplace transform of 0? The Laplace transform of 0 is actually 0. And why is that? Well, if you remember the definition of the Laplace transform of a function is the integral, well, evaluated at s, is the integral from 0 to infinity of e to the minus st times the function. So if I'm trying to find the Laplace transform of 0, this is just the integral from 0 to infinity of e to the minus st times 0 dt. And that's the integral from 0 to infinity of 0 dt. The integral of 0 is 0, so this is just 0. So the Laplace transform of 0 is 0. Okay, so that just gives me, on the right-hand side, 0. Okay, now, here's where we're going to use this formula right here. Now, we have a formula for what is the Laplace transform of the second derivative. We're going to use that here. Okay, the Laplace transform of the second derivative means n equals 2. So this is going to be s squared Laplace transform of f. So Laplace transform of the second derivative is going to be s squared Laplace transform of the function minus, and then the exponent of s reduces, S1, and then this is going to be f of 0. I mean, not f, y, because we're using y. Y of 0 minus y prime of 0. Okay, that's what the formula gives us. Remember, n equals 2. So you stop at the f. If n equals 2, that means n minus 1 is 1. So that's you stop at the f prime of 0. You're always going to stop at 1 less than the exponent 2. So that is the Laplace transform of the second derivative. And that is actually very useful to know because we're going to be using that one a lot. So I'm just going to copy that one here for future reference. The Laplace transform of the second derivative is s squared Laplace transform of y minus s y of 0 minus y prime of 0. And also I'm going to copy the one for the first derivative. That is going to be s to the 1, or s, Laplace transform of y minus y of 0. Okay, these are the first two cases. They come in very handy. Instead of trying to figure out the whole big long formula each and every time, the first two cases, we're going to be using them a lot. So, nice to have them handy. So, all right, those are the first two cases from the formula when n equals 2 and when n equals 1, respectively. Okay, then, now we're going to use that one. This is s L of y minus y of 0. Okay, that is this case, the case n equals 1, minus 2 L of y equals 0. Okay, minus 2 L of y equals 0. Okay, now we know what is s of 0. I mean, sorry, y of 0 and y prime of 0. We have the values right here. So now we plug that stuff in there. So this is s squared Laplace transform of y. Now, y of 0 is 1, so this is minus s. Y prime of 0 is 0. So I'm going to have to write it, which is 0. And then now here, this minus distributed, minus s Laplace transform of y. Then minus and minus is a plus, but y0 is a 1, so plus 1 minus 2 times Laplace transform of y equals 0. Okay, now we're going to, the goal is, remember, the goal is to find y. The goal is, this is our dpq. The goal is to find y, so that means we have to solve for y from this equation. So now we're gonna collect like terms. We want all the y's on the left hand side and everything that doesn't have a y on the other side. So all these have L of y, so I want all of those together. So let's collect them. You're gonna get Laplace transform of y, and then you have s squared minus s minus 2. So that collects all the L of y. And then everything else that doesn't have the L of y goes on the other side. So the s goes to the other side, and the plus 1 goes to the other side, so minus 1. Okay, and now dividing by this, you're going to get that the Laplace transform of y equals s minus 1, all that over s squared minus s minus 2. and that is uh, the Laplace transform of y. So we don't know what y is, we're looking for y, but we know what the Laplace transform of y is. It is this. So you see, now our job is to invert this so that we can figure out what y is, and that is where the difficulty lies. Okay, if you look at the table of Laplace transforms, let me see where I put it. There it is. If you really look attentively at all the formulas that we have here, there is none that looks quite like what we have in this problem. So none of these, I mean, this one is not on the table. So what we're going to do is we have to simplify this then. We have to simplify this. And rewrite it in such a way then that we can either apply the properties of the Laplace transform to simplify it and look it up in the table. So we're going to break it up into easier pieces. Okay, this is where we need to use partial fractions. So this is s minus 1. Let's try to simplify. The bottom factors is s minus 2, s plus 1. So that means this thing is going to break up into partial fractions. These are the denominators, so this is going to be a over s minus 2 plus b over s plus 1. So that's how that breaks up. And then multiplying by, remember this is the same as that. So multiplying by that on both sides is going to get rid of that. So you're going to get s minus 1 equals a, multiplied by this. The s minus 2 cancels, so you end up with this. And the s plus 1 cancels, so you end up with that. Right, basically this is what we did. You take that and you multiply the whole thing by s minus 2, s plus 1. Now this is the same as that, so that cancels. The whole thing cancels. You end up with s minus 1 on the left, and then the s minus 2 cancels here. You get a, s plus 1, and then the s plus 1 cancels, and you end up with b, s minus 2. And now you plug in numbers that will kill most of these. Plug in, let's plug in s equals 2, because that's going to kill this one. It's going to kill the b and leave me only with the a. So plug in s equals 2. On the left, you're going to get 1. And on the right, you get a times 3. That goes. So that means a is actually a third. A is a third. Okay, a is a third. Now, let's plug in the one that kills the a, negative 1. If you plug in s equals negative 1, on the left, you're going to end up with negative 2. That kills the a, and what you end up here is b. Negative 1 minus 2 is negative 3. So that means b equals negative 2 divided by negative 3, which is 2/3. So that is the b. Okay, so we found the a and the b, so that means we found how this Laplace transform decomposes. So the Laplace transform, then written in more basic terms, is a third over s minus 2 plus 2/3 over s plus 1. Okay, so now we have to um, now we can invert to the problem. Okay, so we're gonna say y is the inverse of this. We take L inverse on both sides. Well, the inverse and the L inverse and L cancel each other, so you end up only with y. And then this is the Laplace inverse of this whole thing. 1/3 over s minus 2 plus 2/3 over s plus 1. Okay, but remember what we said, the Laplace inverse is linear, so we can break this up and say this is y equals Laplace inverse of, oops, yeah, 1/3 over s minus 2 plus Laplace inverse of 2/3 over s plus 1. So break it up into the sum, and then you can also take out the constants, this constant outside. So that means y equals 1/3 Laplace inverse of 1 over s minus 2 plus 2/3 Laplace inverse of 1 over s plus 1. And now we're almost done. Now we can look this one. These ones do appear in the table. Uh, now we can look these ones up. If you look at the table, we're looking for something of the form 1 over s minus 2. That's something that looks like that. And if you look at that, there it is. 1 over 1 over s minus a. So this, here it is, where the a equals 2. So if this is the Laplace transform, the inverse, going backwards, is e to the at. In our case, a equals 2. So a equals 2, that means when we invert it, it is e to the 2t. So this is then e to the 2t. And I want you to write somewhere for me which formula we're using. So I'm going to make a note of that in a second. I'm using formula 2, row number 2. So row number 2, and then, no, 2/3, the Laplace inverse of s plus 1 is actually the same formula where the a is now -1. If a equals -1, that becomes s plus 1. So a equals -1, a equals -1 here. So a equals -1, so e to the -1t. And I want you to write somewhere that that's what we used. We can write it here on the side. You could write it here above the equal sign. I use number 2 for both of them. Okay, just write it somewhere so I know that that's how you figure that out. We use formula 2. Okay, and that is the solution. We're done. Y equals y equals 1/3 e to the 2t plus 2/3 e to the -t. Okay, we're gonna do one more example. How to use a Laplace transform method to solve initial value problem. Note that in the previous problem, again, we didn't have to find C1 and C2 or find the complementary solution or any of that. Automatically, once we were done inverting the Laplace transform, we got the constants. We got everything. So that's the nice thing about this. Okay, let's do this one. Okay, so the way we started is again the same. Just take L on both sides. That's it. That's how you start it. So take L on both sides of this. So L, Laplace transform of y double prime plus y equals Laplace transform of sine of 2t. Okay, and then on both sides. Now, um, use the linearity to break this up. So Laplace transform of y double prime plus Laplace transform of y equals Laplace transform of sine of 2t. Okay, now we're going to apply the formulas at our disposal to simplify this. So remember the this one right here, we have a formula. That's a special case of the big long formula when n equals 2. So now this is that. So I'm going to write that. So the Laplace transform of the second derivative is s squared Laplace transform of y minus s y of 0 minus y prime of 0. So that's that. Plus the Laplace transform of y. And now the Laplace transform of sine of 2t. The Laplace transform of sine of 2t, there it is this where a equals 2. So that's going to be 2 over s squared plus 2 squared, which is 4. So 2 over s squared plus 4. So the right hand side is 2, all that over s squared plus 4. Okay. Now we plug in what y of 0 is. They're telling us y of 0 is 2, y prime of 0 is 1. So this is going to be s squared plus transform of y minus y of 0, that's going to be minus 2s. Y prime is minus 1 plus Laplace transform of y equals 2 over s squared plus 4. Okay, now we want to solve for y. So we're going to collect the like terms, that all the ones that have y in there, L of y. So this is going to be L of y. So you have an s squared here and a plus 1. These two that don't have L of y needs to go to the other side. So this is going to be 2 over s squared plus 4. And then I'm moving this. So plus 2s plus 1. Okay, now we divide by this and we get the Laplace transform of y. So dividing by s squared plus 1, we're going to get 2 over. So that's going to go on bottom with s squared plus 4. So s squared plus 1, s squared plus 4, plus, and then this gets divided by s squared plus 1. Okay. Now, if you try to look up either of these two terms in the table, you're not going to find either of them. So that means we're going to have to do um, partial fractions for both. Okay, we have to do partial fractions for both. Okay, we're gonna have to do that in a separate piece of paper. I'm gonna do this in a separate piece of paper. I'm gonna put it here. Separate piece of paper. Okay, so we're gonna do it in a separate piece of paper and then come back here because doing the whole thing here is gonna kind of disrupt the flow, the continuity. So, okay, so let's do that. We're trying to do partial fractions for both of these. So first for, let's say this one, for 2 over s squared plus 1 s squared plus 4. This is going to be a s plus b over s squared plus 1 plus cs plus d over s squared plus 4. Okay, because this is these are going to be the denominators because these are the factors, and then because they're irreducible, what goes on top is a polynomial of degree 1 less than the one on the bottom. So it's going to be a polynomial of degree 1. So that's what we have put, that's what we put as plus b. And then same for that one. Okay, then you multiply both sides by this, and on the left you're going to end up with 2, and on the right you're going to end up with a s plus b, and the s plus 1 are going to cancel, so s plus 1, s squared plus 4, plus cs plus d, and then the s plus 4 is going to cancel, so you end up with s squared plus 1. Okay, now you plug in something that is going to kill at least some of these. Let's see, we can plug in I. If you plug in I squared is going to be negative 1. Negative 1 plus 1 is 0, so all of that is going to get cancelled. So you only end up with 2 equals AI plus B, and then again I squared equals negative 1. Negative 1 plus 4 is 3. And then this is going to be 2 equals 3b, put in the real part first, the part that doesn't have an I, plus 3i, 3ai. Okay, so then you have this equation, and you can set the real parts equal to each other and the imaginary parts equal to each other. This side doesn't have imaginary parts, so that means that 3a equals 0, and the real parts equal to each other. So you get, you're going to get that 2 equals 3b, and 0 equals 3a. Which gives you that a equals 0 and b equals 2/3. That gives you a equals 0, b equals 2/3. Okay, using that, we're going to simplify this equation. So that means that 2 equals, we found that a equals 0, so and b equals 2/3. So 2 equals 2/3 s squared plus 4 plus cs plus d equals s squared plus 1. Okay, that's simpler. And now we're going to do the same thing to figure out what is the c and the d. So now we're going to plug in s equals, now we want to, let's say, kill this one. That's going to work, yeah. So we're going to plug in 2i, because 2i squared, well, you get 4 and I squared, which is negative 1, so you get negative 4. So when you plug in 2i here, that gets killed off, that goes, and you end up with 2 equals c times 2i plus d, and then here 2i squared again is negative 4. Negative 4 plus 1 is negative 3. So now this is distributing the negative 3 and putting it first with d, because that's the real part, and the part that doesn't have, that has the imaginary I, is going to be negative 6 ci. Now setting the real parts equal to each other and the imaginary parts equal to each other, we're going to get that 2 equals negative 3d, and setting the imaginary parts equal to each other, well, the imaginary part on the left hand side is 0, negative 6c, So that gives you that d equals negative 2/3 and c equals 0. And now we found all of them, a, b, c, and d. So that tells us then that 2 over s squared plus 1 over s squared plus 4 equals a, which is 0, b, which is 2/3, over s squared plus 1 plus c s c0, and d is negative 2/3 over s squared plus 4. Okay, so now let me box this up because we're going to be using this. Okay, now we have to do the same thing for the other term that we need to invert. So now we broke that one up. We're going to need to break this one up. But that one is actually easy. You don't need partial fractions for that one. It's already done. You see, I mean, that's partial fractions. That's a partial fraction. When you have a partial fraction over s squared plus 1, the top has to look like this. A linear term of degree 1, as plus b. And that one is already like that. So that means the partial fraction is already done. All we have to do is actually break it up. So how are we going to break that up? Well, this is how we're going to break it up. And I'm going to copy it here. So it is 2s plus 1 over s squared plus 1. So the problem is this is still not, this does not appear like that on the formula sheet. So we need to break it up. So we're going to break it up like this. This is 2s over s squared plus 1 plus 1 over s squared plus 1. And this is actually 2 times s over s squared plus 1 plus 1 over s squared plus 1. Now, both of these things are in the table. So that means this is now good to go. This is on the table, that's on the table, that's on the table, that's on the table. So now everything is on the table of Laplace transform. So now we are good to go. Okay, so it takes some quite a bit of work sometimes to put this in ready to go form in order to look it up in the table. But it's all a lot of algebra. Okay, so let's rewrite this using the decomposition that we got. So this is 2/3, and I'm gonna put the 2/3 in front. Okay, so this is what we have: 2/3 over s squared plus 1. So I'm just gonna put the 2/3 in front and put a 1 in there. So this is 2/3 times 1 over s squared plus 1 minus, and do the same for the next one, minus, I'm going to put the 2/3 in front and the minus, and then put a 1 in there. Because that's the way it appears in the table. 1 over s squared plus 4 plus 2 times s over s squared plus 1 plus 1 over s squared plus 1. Huh. Note that there's a little bit of a, these two are like terms. We can probably, yeah, we can combine those two, make this slightly simpler. So those two are like terms, these two. So let's combine them. This is 5/3. 2/3 and one is 5/3. So 5/3 times 1 over s squared plus 1 minus 2/3 1 over s squared plus 4 plus 2 times s over s squared plus 1. Now these two are not like terms, okay, because that has a variable on the top and this one doesn't. They're not really the same. They're not alike. But these two are because they both had a 1 on top. Uh, okay, and now we are ready. Now let's invert. Y equals the Laplace inverse of all that. Well, we can break it up into each piece. So 5/3 times 1 over s squared plus 1 minus, and you can actually pull out the constants. I should have done that, but I didn't. Minus 2/3. I didn't do it for the first one. I'm going to do it in a minute. Plus 2 Laplace inverse of s over s squared plus 1. Okay, pulling out the constant, this is 5/3, and now the constant is out, we can ignore it. And we'll just worry about inverting 1 over s squared plus 1. Okay, that we look up on the table. We're looking for something that looks like of the form 1 over s squared plus 1. 1 over s squared plus 1. And it is this one right here with a equals 1. If a equals 1, then this will be 1 over s squared plus 1. Okay, so it is this one. Inverting it, you get sine of 1t because the a is 1, so sine of t. So inverting that, this is sine of t. And we made use of number 5. Okay, we made use of number 5 for this one. Okay, then this one, uh, this one is going to be a little bit of trouble, so I'll tell you why in a minute. But let's do this one. This one plus 2, and then we're going to look this one up. We're looking for s over s squared plus 1, s over s squared plus 1, and it is right there, where a equals 1. S over s squared plus 1. A equals 1, so that means it is a cosine of 1t, cosine of t. So that one is going to be cosine of t. And that is number 6. Alright, and now the term in the middle is going to give us a little bit of a trouble because those two appear readily on the table. This one does not, unfortunately, because so it is of the form 1 over s squared plus 4. There's no variables on the top, so that's important. So the only two that might look like that are these ones. It cannot be the 6 because it has a variable on the top, this one. So it really is a constant. What I have in this is a constant on top. However, look at the problem. The constant is related to this constant right here. That constant that is at the top is the square root of this constant on bottom, or in other words, the constant on bottom is the square of the constant on the top. So that has to be the relationship. It has to look exactly like that. The constant on the bottom that is being added has to be the square of the one on the top. Or the one on the top is the square root of the one on the bottom. Either way, that's not what's going on here. 4 is not the square of 1, obviously, so we need a 2 in there. We need a 2, otherwise we cannot invert it like as is. We need a 2, and then it's going to match exactly this one. So we need to put a 2 in there, Alright, we're going to need to put a 2 in there. But if you put a 2 in there, we need to get rid of it. So you can put a 2. You can either do either of the following two things. You can move that 2 there, borrow it, and put it in there because we need it. Or you can just put a 2 there and then multiply by half outside just to cancel that, which is what I'm going to do. So I'm going to put a half. And then this is a 2, s squared plus 4. Okay, now it's ready. And now in the next step, I can invert it. I'm going to cancel those as a third. So this is going to be 5/3 sine of t minus 1/3. Now it matches perfectly, and it matches perfectly with that one, which is number 6. Sorry, with number 5. The top is a constant, is number 5. So now it matches perfectly. We're using 5 again. So it's going to be another sine, a sine of 2t this time, because the a is 2, plus 2 cosine of t. Okay, and that is the solution of the differential equation.